For more information, please visit SGMAK Associates website.
In this module, we define experiment outcomes, event, and how to estimate probability of an event. We perform an experiment and observe the outcome. The experiment may be as simple as tossing an unbiased coin and recording the outcome, head, H, or tail, represented by capital letter T. The outcome may not be predicted with certainty, but we can describe the set of possible outcomes. With increase in repetitions of the experiment, as you perform the experiment many times, certain patterns in the frequency of outcome occurrence emerge. The set of all possible outcomes is called the sample space. We perform an experiment, we record all the outcomes, the set of all possible outcomes is called the sample space. A discrete sample space is one with a finite number of outcomes or countably infinite number of outcomes. A continuous sample space has non-countable number of outcomes. Let us look at a few examples. We're tossing an unbiased coin and observe the up face. The sample space will consist of H or T, the head or a tail. You're tossing a fair coin 3 times and you observe the number of tails. So tossing a coin 3 times, the number of tails could be 0, 1, 2, or 3. So sample space consists of these 4 elements or 4 numbers, 0, 1, 2, and 3. The experiment is tossing a fair coin 3 times and observing the sequence of heads and tails. The sample space, since each coin can give 2 outcomes, either head or a tail, and there are 3 coins, or tossing coin 3 times, so there are total 8 outcomes in the sample space, and they are recorded here, starting with all head, then 2 heads, then 2 tails, and all tails. The experiment is we take an electronic component, we manufacture it, and put it on live test, and wait until it fails. We are measuring the time to failure. The sample space consists of all measure of times. Time is non-negative. Let's look at another experiment. We are tossing a pair of dice and you're observing the up faces. So the dice has 6 faces and we are tossing a pair of dice. So up faces, so we have 6 times 6, 36 outcomes as represented in the next table. And if you look at the first number, each row, the first number represents the face from the first dice and the second number from the second dice. If you look at the diagonal element, that shows all those outcomes where both faces show identical number. Let's look at another experiment. Railway carriage body is fabricated with a large number of spot wells. After fabrication, we inspect each well and the total number of defectives is counted. So the sample space is as follows. It consists of numbers 0, 1, 2, all the way to capital M, where M represents the total number of wells in the door. Let's look at another experiment. We are measuring the volume of chemical produced per day in a plant. It ranges between a minimum value and a maximum value, which represents the capacity of the plant. So select a day randomly and select the volume produced. We record the volume produced. The sample space consists of all numbers between the lower limit and the upper limit, which is represented by A and B in this example. Let's look at another experiment. We have a pallet of 8 castings. We know of those 8 units, there's 1 defective unit and 7 good units. 4 castings are randomly selected without replacement and inspected. So sample space will have 5 outcomes where n represents a non-defective and d represents a defective item. Now let's define an event. An event represented by E, capital letter E, is associated with the sample space of the experiment. Typically, one or more outcomes is associated with an event. Let's look at a few examples. We toss a fair coin, and the event of interest is toss yields a tail. So in this case, we only look at the outcome that has outcome tail in this case. We toss a fair coin 3 times, and the event is all coin tosses show the same face. So we have only 2 outcomes in the sample space, all heads and all tails. They support that event. We toss a pair of dice, and up faces show the same numbers. So as we described before, the diagonal elements of the table, there are 6 of them, they will support this particular event. Testing an electronic component and the time to failure is greater than 1500 hours. So in this case, all values of time measured as the time to failure that are over 1500 hours. If a sample space is finite and has equally likely outcomes, then probability of an event E is represented by probability of that event equals number of outcomes favorable to the event divided by the total number of outcomes in the sample space. So it's a ratio of number of outcomes favorable to the event divided by the total number of outcomes in the sample space. So probability of an event is a number between 0 and 1 for each event defined on the sample space. Let's estimate the probability of each event defined earlier in this document. Probability of getting a tail when you toss a fair coin is 1/2, one outcome favorable out of total possible 2 outcomes. Toss a fair coin 3 times and all the tosses give the same face. So you have 2 out of 8 outcomes favorable to this event. So you have a probability measure 2/8 or 1/4. Tossing a pair of dice and the up faces show the same number. In this case, as described before, we have 6 outcomes in the sample space that are favorable to this event. So probability of this event will be 6/36 or 1/6. Next event, we test an electronic component and the time to failure is greater than 1500 hours. In this case, we have a continuous sample space. Now we need to define the time to failure to solve this problem. If we define that as an example as a uniform distribution with parameters 1200 and 1800, that means minimum time is 1200 hours and maximum time is 1800 hours, then probability of this event is given by 18 minus 1500 divided by 18 minus 1200 is 1/2. So probability time to failure is greater than 1500 under this situation is given by 1/2, 0.5. We also estimate the probability of an event based on relative frequency of occurrence of the event when the experiment is repeated. So if an experiment is repeated n times and the event A occurs n sub A times, then f sub A given by n sub A over n is called the relative frequency of event A. As the experiment is repeated, the numerical values of f sub A stabilizes and approaches to the value of the probability of event A. So the probability of event A is defined as n sub A over n and the limit as n approaches infinity. In reality, we accept something less than infinite repetition of the experiment. So as the experiment is performed many times, this ratio converges to a value which you define as the probability of that particular event. This module provides the basic element that must be understood to be able to estimate the probability of an event. Your attention must be paid to the definition of individual elements such as the experiment, the outcome, founding the sample space, definition of the event, and then the probability of an event. These are all important concepts. Contact us if you need clarification.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.